All right. So even if you don't have any questions about your homework, I'd appreciate coming to speak to me. That's what I'm here for. Talk about anything astronomical here with this one. All right, and pick up a revised version of problem set 4 if you picked one up earlier. This one has, I deleted problem 3, which we haven't really covered yet. So we'll talk about that later. Okay. Come on. Aha. All right. This thing decided not to work today. Okay. So we're going to start talking about the planets now, the Earth-like planets. The Sun has the Earth. We know the Earth has liquid water, et cetera, et cetera. Okay. So before we talk about that, I want to talk about a leftover that we didn't talk about last Thursday, and that is radioactivity on the Earth. Now, some of you have learned about radioactivity in your chemistry courses or physics course you might have taken. But you know that radioactive material can release decay with considerable energy. And if that passes through you and interacts with your body, it can cause some damage. All right. So there are 4 types of radiation. This is something discovered early in the 20th century. Scientists didn't know what the hell these radiations were, so they just named them alpha, beta, gamma. Then they realized there's another particle too, the energetic neutrons. All right, so these alpha, beta, gamma rays were first seen. They really had no idea what was going on. But now we understand it. Now, for beta and X-ray and gamma rays, we measure the dosage. If this radiation is there, if radiation is shining at you and you're getting hit by it, we measure that in a dosage called Roentgens. Roentgen was one of the first scientists who worked on this. So it's called a Roentgen. And we measure REM, Roentgen equivalent man. So the REM is equivalent to 10 to the minus 5th joules of energy per gram of body mass. So it's a certain rate at which this stuff is shining at you. And it tells you how well you're cooked. All right, now, here are some background levels. And most of these are not numbers to remember. If we're just walking around Berkeley or anywhere, we get 300 millirems a year. That means we get 3 10 to the minus, this is 0.3 10 to the minus 5th joules per of energy deposited per gram of weight. So, all right, is that a lot or a little? All right, so what is this? A millirem, of course, is 1,000th of a rem. Now, 200 millirems per year is what you typically get from radon emission from the atmosphere. If you have a basement that's tight in the East Coast, a lot of people have a serious radon emission from radon leaking up from the Earth and then being trapped in their basement. If you are near radioactive rocks, such as granite, you'll get 0.3 millirem per year. If you're near potassium-30 or carbon-14, you'll get 40 millirems per year. These are natural backgrounds. They're not that dangerous for you. It's really very undangerous. All right, but there are other places where it's considerably high. If you smoke something, it gets 60 millirems, that won't hurt you. All right. The radioactivity won't hurt you, but other things will. Now, if you want to really worry about radiation damage, you don't want to be an airline pilot, an airline stewardess, because you can pick up typically 1,000 millirems per year just from being in a high altitude for a long time. So at high elevation, there is less blanketing of air to block out the cosmic rays, and that means that at high elevation you will see a stronger background. So if you're really afraid of backgrounds, you should not live in Denver. Very bad place to live. And you shouldn't fly in an airplane. You should stay low. Okay, but these are real issues. Don't live in Denver. Avoid flying in airplanes. Now, in 1997, the United States launched this Cassini satellite. It was a giant satellite. It really took a lot of power to get it there, and then we used the slingshot method to get it from Venus to Earth to Mars to Jupiter and finally to Saturn by all these slingshots. Now the slingshot, when it went by the Earth, was pretty close. It was above the atmosphere by not that many miles. If they had mistimed it, if the thing were out of control, perhaps it would have crashed into our atmosphere. So I got a call one night before this thing launched by someone who was concerned. He said, this is crazy. Why are they sending this thing coming by the Earth and it's going to bring all this radioactivity and it's too dangerous to the Earth. All right, so how dangerous is it? All right, now we already know that solar power is not practical if you're going to be out at orbit of Saturn. I mean, you just need too big a solar sail to collect it. It's too big, so it won't work. NASA realized that, and therefore they designed something called a radioactive thermal generator, RTG, provides electrical power. It's a very unusual type of device. It's not something you can have on Earth applications. It's very expensive because they use extremely rare isotopes of a rare element. They use the rare isotope of plutonium-238. Normally, plutonium is 239. 238 plutonium is very rare. This stuff includes 72 pounds of this stuff. This stuff is not found everywhere. It's only made in a few reactors in the United States. I think it's in South Carolina where this stuff is made. It's not something you can have. You can't go down to the hardware store and pick up 20 pounds of plutonium. It's just not available. All right, so what did they do with it? All right, so this is a lot of stuff. So you might wonder, this thing came back to Earth. We know it slingshot off the Earth. All right, now it was en route to Saturn at this time, but the time when it slingshot around the Earth, it was already moving pretty fast. It approached the Earth at 18 kilometers per second and slingshot around us, or the Earth's orbit could give it another 25 kilometers per second. It just makes it accelerate, and so that's good. They wanted that to happen. It's a lot better than a big rocket. All right, so how does this work? Now, suppose the satellite just disintegrated totally. We misjudged it. They didn't time it, and they had the thing aiming at the Earth, and the thing hit the atmosphere and just blew up. Okay, what would happen? What effect would it happen? Well, if the whole thing disintegrates and turns to dust on the atmosphere, suppose you you eat the dust that falls over 1 square meter of ground. Just go down and lick the dust so you get it all. Okay? That will increase your radioactivity by 1/10 millirem per year. All right, that's how much radiation you would pick up. And to calibrate, that's about half the radiation you get, the extra radiation you get because you have a gas stove at home. And the gas has a little radioactivity in it, and as it burns, you're exposed to it. So that's not a problem, therefore. There was another case like this. You've got to have equivalent doses. There was concern about a alpha-emitting source at Lawrence Berkeley Lab, and somebody said, gee, these children come near there every day. We can't allow them to be near this radioactive source. It's too dangerous for them. And so scientists looked at the issue, how radioactive it was, and they said, well, all right, if we want to know what the dose equivalent would be to this, the children drive up on the road on the way to Lawrence Hall of Science, beautiful museum with dinosaurs and stuff. Anybody been there? Okay, you see these neat dinosaurs and other games you can play. A lot of children go there. So what dosage would you have to raise? How much would you have to change their dosage to see how dangerous this is? And the scientists worked out that it is equivalent to raising the platform of their chair from here up to here. You raise their chair by 1 centimeter. Now that puts you higher in the atmosphere, where you get a higher rate of radiation from the atmosphere. So, well, you know, that's a nonsensical comparison, but that's what it amounts to. Radiation can be measured most of the time. Doesn't mean it does a damn thing. It is dangerous if you eat it, but don't eat it. You know, plutonium is nasty, poisonous. You don't want to eat it. Chances of a crash were hard to calculate. Plutonium was, you know, the Cassini mission went by. Everybody forgot about this because Cassini went by the Earth, went by Mars, Jupiter, and finally made it to Saturn. And there were no problems, so they shut up. But that was an issue. They made it to be an issue. It wasn't really an issue, but they made an issue out of it. All right, so now radiation is incredibly invasive, and we are protected from radiation damage by the atmosphere above us, which serves as a blanket to keep us warm and to shield out all the ultraviolet radiation, all the X-rays, and high-energy particles as well. And if we ever go to Mars, as people have suggested, you go out of the atmosphere, you're on a thin spacecraft, traveling to Mars for a year, or however fast you can go. You're traveling to Mars, and unprotected from cosmic rays. There is a risk, a very serious risk, that the sun will erupt and send out a lot of junk that will go through and make a crispy critter out of you, and you don't want to be in such a situation, and you can't do anything about it. So it's not sufficient to have warning from people from Earth to say radiation damage or radiation is going to get here. What are you going to do about it? Well, they suggested that you have in a spaceship you have a protected room you go to. But a protected room means it's heavy metal, and it becomes heavy to lift, to launch it. It's not very practical. A real protection is a full atmosphere. That's a protection. But replacing that with a piece of metal is hard to do. So it's not recommended. Okay, you can see all about this in a web page if you want, but it's not required. Okay, so if you finally got to Mars, I don't know if you'd ever get back. It's a long time. You know that astronauts who are in space for a while have tremendous trouble of losing the calcium in their bones, which during the weightless encounters, the calcium washes out of the bones for some reason, and it doesn't get. They don't have any exercise, and then when they get back to gravity, the weight of themselves is too much for them. So if they're out in space for a while, it's very hard to come back. You know, lots of science fiction stories about older people or people who are working in the belts, the asteroid belts, don't want to go back to normal heavy Earth gravity. They can stand Venus, or they can stand Mars, excuse me, but they can't stand the Earth. Well, that's just science fiction, and that isn't. Who knows what will happen? All right, so now I want to talk about the Earth as an astronomical body. All right, so let's talk about this and see what happens. The Earth is a beautiful object. It is the only planet we know that has life on it, that we know of right now. It's a gorgeous ball. This is, of course, seen from the moon.
Why is the other half not visible?
Why is the other half not visible? What happens? Anybody? Why is this Earth? You know, the Greeks were not right. The Earth is sort of round, except for a big section chopped off down here. Why is the Earth not seen?
Is it because it's in the shadow of the moon?
Not the shadow of the moon. Sorry? The sun. Yes, if the sun doesn't shine on it, you won't see it. It's night in the other parts. Okay? All right. Right. Okay. So the size of the Earth, we know is 6,400 kilometers. That's a result. That's not Eratosthenes' measurement, but that's a result we know from him. The mass. How do we measure the mass? Well, we know the acceleration of the Earth. If you you drop a ball here, you measure this acceleration, little g, and it's equal to gm over r squared. R squared is given here. Gm is a quantity you know. Now, gm, usually the problem is you measure gm, and it's hard to separately measure g and m. But it is possible to do it, and this has been done, and you can look up in a book what is the value of g. Google will tell you right away, or something else. All right, so g is this number. All right, so you can solve the equation. M is the inversion of the equation. G, r squared over little g, over big G, and you look up the value of g. Determining g is difficult. It's the most famous way of doing it is something known as a Cavendish torsion balance. That's something for physics students to learn about. You don't have to worry about it. But it does provide a measurement. The modern value is a number like this, all right, which you can look up. All right. And we put it together, and you end up with a mass of 6 × 10⁻⁴ grams. Okay, fine. Now, what is that good for? Now, if we want to understand how the Earth works, well, how does one do it? How do geologists know all about the interior structure of the Earth? And the answer is they study waves. The waves are generated by earthquakes, someplace on a spot here. Some earthquake comes here, and it sends out a lot of rays, and then you see it bouncing over here, and you have listening stations all around the Earth, and you follow the listening stations and you find out what's going on. Now, what's going on? Well, there's a couple things. First of all, there's something called a pressure wave, where you push on something back and forth, and it responds, just like a spring responds, or like the air responds when you talk. We talk, and I send the signal out to you by a pressure wave. Another type of wave is a secondary wave, and this is where I shake the spring sideways, and the perturbance it follows the head, and it's just the same. Now, here are secondary waves emitted, but one characteristic is the secondary waves do not propagate in a liquid, so they won't work. All right, so that is a problem. They won't do that. The other point is that the primary wave bends in the solid material, in this liquid material. And so these waves all travel in different directions. The geologists know all about this. And from this, they have put together the structure of the Earth. They know quite a bit how this works. It's all from these waves. And of course, you don't depend on just one earthquake here. There might be earthquakes all over the place, and you study them carefully. All right, so the interior structure, they can use not only earthquakes, but you can use nuclear bombs, nuclear tests all over the Earth. This was a big deal when you were infants. I think you don't remember that, but the United States and Soviet Union were always blowing up these stupid nuclear weapons for testing purposes, they said. Now I don't think one's been tested for 20 years, or I don't know, a long time. All right, so this is how you determine interior structure. And with these two types of waves, pressure waves, longitudinal waves, these are just going back and forth. And the S waves, there are stress waves, secondary or stress waves for S. They're transverse waves, and they don't travel in a liquid. Okay, fine. So your detailed study leads to a very detailed picture. We know the following components. First of all, we have a thin atmosphere. Everybody knows that. We have a fairly thin, measured in terms of the thickness of the Earth, it's pretty thin continental crust. It's about 10 miles thick. That's it. And remember, you're comparing it to 6,400 kilometers. So it's a small fraction. All right, then there's a plasma mantle. Now, we say it's plastic. A plastic flows slowly. A plastic is more like a liquid than a solid. It's a liquid because it will flow. It doesn't matter. For this purpose, it doesn't matter whether it flows fast or slow. It flows slowly. And it flows in these so-called convective cells. We'll talk about them. Then there is a molten iron core. This is way inside the Earth. A section of the Earth is known by the seismologists to be iron core and liquid. And then inside of that, there's a solid iron core. So inside this liquid core, there is a real small core. Okay. Now, the density at the top of the atmosphere, density of the entire planet is 2.7 grams. At the top, I'm sorry. No. Okay. All right, the density at the top is 2.7 grams per cubic centimeter. That's the density of basalt or granite. The density of material in the center of the Earth is quite a bit higher. It is, it's approximately 13 grams per cubic centimeter. What the hell? Boy, this thing, I got to change my battery. 13 grams per cubic centimeter. Can everybody see that? I can't even see it anymore. All right. 13 grams per cubic centimeter. And the material is made of iron and nickel. Iron and nickel is a metal. You take it by itself and you weigh it on the top of the Earth, it's 8 grams per cubic centimeter. But it's 13 grams per cubic centimeter in the center of the Earth. Why is it so much denser in the center? It's compressed. It is heavily compressed by the weight of everything on top of it that's squeezing the hell out of it. All right? Now, the temperature in the core, we know, is 4,500 degrees Kelvin. And their differentiation, the heavy stuff in the center, lighter stuff on top, is typical. All the planets are like that. And this is what will happen if the planet is molten at one point. It melts and slowly radiates away, but it's in that position and stays there. Okay. All right, so now the core contains a ton of uranium, thorium, potassium, and these are decaying elements. They are radiating heat as they lose energy, and the heat is sufficient, probably sufficient to melt the whole planet. Just melts it. Like, these things that happened in Japanese reactors that melted. All right? Here is the entire Earth would melt from this stuff. All right? Now, if that's not sufficient, the energy that all the material had as it slammed together is also hot enough to melt the whole thing. And so there's no question the planet was molten when it was formed. Okay, now if you look at the details of how these planets are laid out, here is an iron core, here is the Earth, up here is the lithosphere, it's called. That's the crust and part of the mantle, the lithosphere, the mantle, etc. Now if you compare it to Venus, Venus has about the same ratio of elements, about the same everything as the Earth. It's more or less the twin sister of the Earth. Mars is smaller, and otherwise it looks about the same, but we'll see a little bit about it as we talk today. Mercury is somewhat different. Mercury does not have much crust. Mercury has a lot of the core. Why? Why isn't Mercury the same as the other planets? And the Moon. The Moon has less. It's more of the it's less of the heavy core than the other planets. Why is it different? So the planets are all different. And the question is, why is it different? What can we learn by studying the planets? All right, now these, okay. Why does Mercury have a bigger core than the others? That's a question. And probably the answer to this is the mantle material, all this out here, all the red stuff, was evaporated during formation. Or it was hit by another satellite that came in, hitting it fast and just blew the stuff apart. Remember, the formation time is very chaotic as these planetesimals are constantly hitting each other. All right. Okay. Now, finally, in the Earth, these three types of radiation are what I learned in school in the 9th grade or whatever that was. I presume you learned them too. Conduction, convection, radiation. What grade did you learn that? 9th grade, high school. Anybody not learn this? They used to teach it in general science, I think, which I think was a 9th grade subject. You've never heard the terms?
Heard of them, but I've never.
All right. Well, look, here's the idea. Let's start here in the center. Convection. Convection. What is an example of convection every day? When you boil water. In that case, water is heated at the bottom. It flows. The water is so hot it flows up. Why does it flow up? Well, the hot water is lighter than the heavy water. It flows up without. It's not as heavy, so it's going to try to come into balance. It goes up, and then it cools off, and then goes down. Goes up, comes down. Goes up, comes down. And here it is on the Earth. Convective cycles. All right, boiling cycles of the Earth. Now, the Earth, you know, and when you've got a pot that's boiling, it turns over every second. You know, it goes over and over and over. Well, it's a little slower here. This turns over in 500 million years or 50 million years. Same thing. What's a second or 50 million years? Same thing. You know, it doesn't matter. But it's the same physical idea. The Earth is convecting right there. Now, conduction. The air, the water, the Earth gets some heat is brought up to the base of the mantle, and the mantle doesn't really convect. You can't do that to the mantle. The mantle really could conduct the material. I mean, you heat the bottom of the mantle, and slowly the heat will diffuse through it and conduct it out. But rock is a lousy conductor. You know, we got 10 miles of rock there, and you got to work your way through it. That's forever. That won't happen. It'll happen, but very, very slowly. So the rock isn't a very good conductor. Then at the top, the Earth is a certain temperature. We are a certain temperature, and we radiate away the energy of us. So those are three modes of energy transport. Those are the three modes that we will use in this course again and again. All right. The active Earth uses all three modes: conduction, convection, radiation. All right, so you know, we talk about hydrostatic equilibrium. If I have a ball here and I push on it really hard, why doesn't the ball flatten out? The ball doesn't flatten out because my force of pushing is balanced by a force in the ball that's got these little molecules moving around, and they're pushing out, and they push with as much force as I can push out. And we say that is hydrostatic equilibrium. That's what it means. So the Earth is in hydrostatic equilibrium. Stars are in hydrostatic equilibrium for the same reason. All right. Now, if this isn't right, the Earth is somewhat out of, you know, if the Earth is held up by the heat of the inside and then the heat leaks out, the Earth will shrink. Because that heat on the inside is holding up the heavy Earth above it. But if suddenly you put something in there and you leaked all the heat out, the Earth will shrink. All right? It's important to realize that. Okay, so the pressure of the air supply is made by the heat, and that is thermal pressure. Now we had to understand pressure, and it's a little bit tricky because the pressure we will see of objects in astronomy are not always supplied by heat. There's something else that does it. We'll wait till we get there, and I'll talk about it. But just beware that air pressure is not the only way of holding something up. Okay, so if you look at a planet that has been cooling the pressure is diminishing on the outside, and the gravity will win a bit, and the planet shrinks, but it might leave cracks on it. And so we'll look at Mars, and you'll see evidence of cracks on Mars. As the planet cooled down, it cracked the surface. So we'll talk about that as we get to it. All right, so as I said, rock is a lousy conductor of the heat. The reason we have a certain equilibrium temperature has nothing to do with what the Earth is doing inside. The Earth is very warm and it can fry us all instantly. But, it's warmer than lava. But we don't worry about it because we're protected by the rocky Earth. We do worry about the energy in equals the energy out. The energy of the sunlight equals the energy we radiate. So that we have to balance, and we'll talk about that on Thursday. Okay, so if you calculate exactly what happens, energy in, that's the energy of the sunlight, equals the energy out, you get a temperature of 250 degrees Kelvin. And the actual temperature of the Earth is considerably higher. It's 294 degrees Kelvin. That is 20 degrees Celsius. Okay, that's the average temperature of the Earth. So there's a 43-degree difference. 43 degrees different between this and this. And the difference is due to a greenhouse effect. We have a strong greenhouse effect that keeps us warmer. And we will talk about that on Thursday. Okay. Now, the sun's visible light goes through to the solid Earth. Re-radiation is, this is how the greenhouse works. Water, carbon dioxide, methane, and these gases keep us warm. So we'll talk about that later. Okay. Now, here's a question for you, though. Now, when the Earth was young, it turns out that the Earth was, the sun was not shining as brightly as now. The sun actually put out half the energy that it puts out now. Why didn't the Earth freeze? We know the Earth would freeze if you did it now. If you took the sunlight and divided it in two, the Earth would freeze solid. But why didn't it freeze then? So here's some reasons. I don't expect you to necessarily understand, to get this right now, but we'll talk about it. The young Earth was warm for all the reasons I've talked of, and that prevented freezing. The Earth had more carbon dioxide, which later floated away. Our Earth had plenty of methane, which is an even better greenhouse. Or the Earth had tons of CO2, which dissolved in water, making the oceans fizzy. You can get injectors of these things in the water, and you can fizz your water. I have one at home. They're really nice. You put a bottle of water next to it, push the button, and in a few seconds you've got a fizzy bottle. So this thing is another way to do it. All right, I don't. The fellow, Eric, isn't here, so he doesn't have the cards. But everybody, talk to your neighbor about this question, and let's see what caused it. What's the answer?
Like
Either B or D.
All right. Was the Earth so warm that it so warm from its molten time it was molten? Was it so warm that prevented the freezing? No. Okay. The freezing it would have frozen up to 2 billion years ago, and by that time the crust had formed very solid. It didn't do it. Okay, the Earth had CO2, which later floated away. No? Yeah, that's too bad. Okay, that's not right either. We'll see later that CO2 doesn't float at all. CO2 is a gas that's heavy and it sinks compared to other gases like helium and hydrogen, which do float away. Okay. All right. The Earth had plenty of methane, which is even better greenhouse. Yeah, okay. A few people said that. Well, that's a good idea, but that's actually not the story. The answer is D. The Earth had so much CO2, it dissolved in the water and made the oceans fizzy. Now, what do we mean by so much CO2? Has anybody ever been to the Dolomites in Italy? Or have you been the limestone cliffs in England? Or gone in a cave in the United States? The caves are often formed by water percolating through the rock and melting limestone in the cave, and then you can see stalactites and stalagmites, or maybe I don't know which is which. Anyway, one goes up and the other goes down. Anybody know? Stalactites are tight to the ceiling. Right, stalagmites are from the bottom. Okay. Anyhow, all right. But these, they're all made of limestone. Now, what is limestone? Limestone is calcium carbonate. And this calcium carbonate contains enough carbon dioxide in it. All the stuff around the world has so much carbon dioxide, if you took it out and put it in the atmosphere, first of all, the atmosphere would be 40 times larger than our atmosphere now, really thick. Instead of our this thin atmosphere here, it would be a thick atmosphere, 40 times larger. I'm not saying we increase the carbon dioxide level 40 times. I'm saying we take the full atmosphere and increase that 40 times. The carbon dioxide is only, what the hell is carbon dioxide right now? Anybody know? It's less than 1%. I can't remember what it is. Anybody know? It's in the, you can find it on Google. Somebody look it up, you know. Anyhow, it's less than 1%. All right, and I'm saying increase the carbon dioxide about a million times, really a lot. And doing that will bring it, has a lot of, makes the atmosphere very fizzy. Now let's talk about what this means. All right, so the sun's luminosity was about half its present value. Why didn't the Earth freeze? Okay, they've never been frozen from anything related to the sun. The answer, the greenhouse of the Earth was probably incredibly intensive. 40 atmospheres of CO2 were once in the atmosphere, but they all dissipated by first dissolving in the oceans, and you have the carbon dioxide abundant in the ocean, and then it will mix with any calcium in the water, and precipitate out as calcium carbonate. This is the same thing seashells are made of. Seashells make this all the time, but this is without seashells. No life involved. It'll happen anyhow. Naturally precipitating carbon dioxide. Okay, so it's very important that we have the ocean to remove all the carbon dioxide. It played a very important role for us. All right, so the atmosphere of the Earth, as we know, contains oxygen. But the primitive Earth had no evidence of oxygen. None whatsoever. Oxygen was only in place for the last billion years due to plants. Everything in the atmosphere, all the oxygen in the atmosphere is plant life formed. How do we know there was no oxygen in the earlier atmosphere?
Because there was no light.
There's no life, but that's sort of circular.
Okay, true.
Examine the rock.
Sorry?
Can we examine the rock?
Examining the rocks is a good idea. It turns out that if oxygen is in the atmosphere, it will instantly, very quickly, it will oxidize all the iron. Iron will go into an iron oxide. You know, steel beams rust, and over the lifetime of the Earth, they rust real good. Everything rusts. So the oxygen is very reactive, and it will form some chemicals to precipitate it out of the air. But we don't have any evidence of that occurring. So there wasn't any, and they conclude that there was no oxygen in the air in the early Earth. Okay, now, let's set that aside for a minute. And now I want to switch to a question of what we see on the Earth. The Earth has a magnetic field, substantial magnetic field of a dipolar shape. Here's a dipole, the North Pole, South Pole. It has magnetic field lines that are like this. A dipole can be made by taking a battery around a coil of wire. A coil of wire is this wrapped up around, and and you run a current through here, and it will generate a magnetic field. It looks much like the Earth's, with a North Pole and a South Pole. That magnetic field is something we've known about since the early part of the 19th century. Okay. Now the Earth has its own magnetic field, and it looks dipolar. There's a region up here where the magnetic field lines seem to emerge from the Earth, and they go back in the Earth in the other hemisphere. Now, the way this is generated is you've got to have currents moving around to make a magnetic field. So on the Earth, we say the outer core, which is a liquid region, can have currents in them. We call it a dynamo action. Don't worry about dynamo, but that's just what they're called. The field extends way out in space. And what happens to high-energy particles that come in from the sun or elsewhere, if their energy is right, they respond to the magnetic fields. And the magnetic field makes the particle move sideways. And what will happen is it gets close to the pole and it spirals round and around. And that's an effect we see on all the systems, and we expect it to be there. These high-energy particles loop back and forth, and they produce the aurora. How many of you have seen the aurora?
The actual one?
The actual aurora. Okay, what was it like? Sorry? Okay. All right. Well, most of us, in California here, we're too far south to usually see the aurora. Besides, the lights are too bright. But it's generally not visible here. You have to go further north, where the magnetic field lines emerge from the poles, okay, or further south. Now let's take a look at this. All right, the sun sends particles which are moving pretty fast. They'll hit the magnetic field of the Earth and are deflected by it. All right, but sometimes they get in close to the Earth and spiral around to get way down in here and spiral around, and then they can loop back, but they do lots of things. And they produce, these are trees, and here's an aurora overhead. Here's a view from a satellite. The wind is impressive. These auroras are really beautiful. Let me show you another one. Okay, here's a picture of the Earth with an aurora coming. Note the structure there. They're all flowing into a point there. The aurora is not fixed in time. It varies. This is not really bright, but that is it. That is the aurora one evening, taken from a satellite.
How come it's green?
Why is it green? It's green because one of the prominent lines is what happens is these particles, the energetic particles from the sun or elsewhere, they slam into the atmosphere. When they hit the atmosphere, they can excite it. They'll excite the atoms in the atmosphere. Line of, if they hit an oxygen atom, the lines that they can excite are, one line they can excite is in the green portion of the spectrum. And the green portion of the spectrum then radiates as it comes out. It'll shine, it's hitting the green, and then it comes out in the green light. It's pretty impressive. These are beautiful exhibits. All right, so this is the aurora. Now, what this tells us is that the Earth, indeed, has a liquid core, and the liquid core produces the aurora. If it was a solid core, it wouldn't have, there's no mechanism in there to make the magnetic field. Without the magnetic field, you will not see an aurora. Some of the planets we will study do have aurora. They do, and therefore they have magnetic fields in them, and therefore they have liquid cores. Some of the other planets don't. So we'll talk about this as we go along. Okay, now the convection. Convection is a layer. This whole layer is below everybody, and continents are like leaves drifting and spinning in a pond of water. Pond of water being tousled by the convective cells, and the continents just are along for the ride. But the continents consist of Berkeley that has right down through the center of it, in fact, right through the center of campus, is a region where the earthquake zone is located right there. Why is an earthquake zone right here? Well, historical. But what's going on? These earthquakes are being pushed by the material underneath them. You want to stop the earthquakes, then go in the center of the earth and stop the core. That's the problem. These convective cells are what cause the Earth to have the earthquake zones. Now, we also know that there are hot spots on the mantle. Now, if we look at the mantle, there's a hot spot some of them are very famous. Who's been to Hawaii? Who's been on the Big Island? Okay, the Big Island is the most recently formed of the Hawaiian Islands, and they are from age, they date from young Mauna Kea all the way back to very old islands in the northwest. And you can date the Hawaiian Islands, and they're a perfectly linear relationship. You go back, and what is that telling you? It's telling you that there's a hot spot on the Earth, that the mantle is hot, is boiling up there, and above it, a crust is supplied by the hot material, and it constantly builds planets. It builds volcanoes. So the volcanoes on the eastern side are young, on the western side are old, and the western side was, if the volcanoes, here's the hot spot, it's just measuring how long it's been. And it's moved, I don't know, several hundred miles in the last 500 million years. Okay, so continents are like leaves spinning in the surface of a pond. All right, now let's take a look here. Okay, so here is the Earth, and here are some convective cells underneath it. And so I'll turn this on, and as the convective cells turn, material comes together, is dragged together here, here, and here, and shoving mountain ranges up in the region where two of these cells are coming together and cracking the material and causing it to go down where the material is pushing away. It's making it thinner. These are mountain ranges. The mountain ranges and the floors of the ocean. All right, and this is how all these features are formed on the Earth. But you've seen all this before, I presume. Okay, the crust is squeezing together or extending, and the result is as we've seen. Okay. Yeah. Okay, the convecting cells builds mountains on the Earth. That much we know. All right, next, let us look at the moon. Here are 3 pictures of the moon. One picture this is the moon we can see, but this is the moon we can't see. And it looks rather different. The back of the moon has enormous, it doesn't have these seas all these seas here are lava that flowed into the moon. The lava is old. Everything on the moon is billions of years old, 4.5 billion years ago. But here is all rocky. It's high rocky. Okay. The density is much lower than the Earth. Why? And the moon's very large. And did collision form the moon? All right. Why not? Why doesn't this look like the Earth? Does this look like the Earth? Well, it might. The Earth might have looked like that 4 billion years ago. But the Earth has a weathering action. And the weathering brought it all down, making it flat. Okay. Why does the moon always have the same face looking at us? Why don't we see the back of the moon ever? It orbits in a certain way, but why does it orbit why is it orbit always facing the Earth with the same face? You think about it, it is a puzzle. Why does that work? Why? All right? Now, the reason for this is something we call tidal braking. Now, let me show you what tidal braking is. Now, tidal braking here's the Earth, here's the Moon. Okay. Now let's worry first about the Earth, the influence of the Moon on the Earth. So the Moon is going like this. All right? And we know at the same time that it raises tides on the Earth. I'm going to draw them like this. These are tides. And the tides should point to the gravitational field of the Earth. All right? Now the Earth is rotating. It's rotating like this. All right? Now what does that do? The rotation is going to pull the Earth's surface until it looks a little different. Now, the tides you'd think would point right at the Moon, but actually the rotation of the Earth makes them, I'm drawing very exaggerated tides. Okay? And there's an angle theta between them. All right. So the rotation of the Earth pulls the tides ahead of it. And now we see that the Earth presents to the Moon an unequal distribution. The distribution here and here are very different. For example, this piece of the Earth feels the gravity of the Moon. What does it do? It attracts it, pulls it back. This one feels it too, but it's back here is very weak. It's unable to pull it. And this, what does this do? It's acting as a drag on the Earth. It slows down the spinning of the Earth. The Earth was spinning. We can tell by corals, if we look at the corals in ancient days, you can tell that the Earth all right. 500 million years ago, the Earth, the day was 22 hours long. All right? Now that was something we can measure off corals where you can see a daily count and a yearly count. You can see how much has grown. And it's amazing, but this is actually possible. 22 hours for a day and 400 days per year. So the Earth was spinning faster, and that meant there were more days in a year because the time it took the Earth to go around the sun was the same. All right? It was slowed down. So that meant that when the Earth was born, it probably was indeed spinning faster than 22 hours. It probably was spinning, it probably rotated around and spun in 10 hours or something. 10 hours is very fast, but it slowed down to 22 hours. Now, we're slowing down, and so should the moon slow down. We're slowing down by the tidal action of the moon, and so the Earth acting on the moon, generating moon tides on the moon, even though the tides are not liquid, the tides are solid, the tides on the moon should slow down the moon's rotation. Slow it, and it slowed it so far that the moon doesn't rotate at all. It just rotates. It's exactly in a position where it always presents the same face to the Earth as it moves around. It doesn't spin because it was slowed down by tidal friction exactly the same way the Earth is being slowed down by tidal friction on the moon. This is something we will see is incredibly common in the solar system. There are other examples of this. For example, Mercury. Mercury is a planet close to the sun. It's the closest planet. And it is locked to the sun. The same way the moon is locked to us, Mercury is locked to the sun, going around like this, always facing the sun. The same one side of the sun, one side of Mercury is in the sun, the other side's in the shade. Always. All right? That is because that for the same reason it was tidally locked to it. For the same reason. And that's to be expected. We see examples of that, and we expect them to be locked all the time. Okay. All right, so the moon now is dead. We say it's dead. It has no volcanism, no magnetic fields of note, no seismic activity. We know that the core of the moon has frozen solid. It's all completely, it's completely frozen. Now, that's not surprising. It's a much smaller object than the Earth. And we know that small objects will freeze faster than a large object. And so all the heat of the moon basically has gone away, and it froze. There's nothing left on the moon. Frozen body. And so we tell that the Earth is still alive because of its magnetic field, and we will see what the case is for other objects as well. All right, the core of the moon is frozen. All right, why is it so different front to back? All right, there are fewer craters in the seas here. The seas were molten. There's a race to record 4 billion years ago. These craters covered the whole planet. But radioactive heating melted the planet, and then it flowed and filled in the craters over there. So we think the moon has been dead for 3 billion years. That's a long time. All right, now let's go to some other planets. Suppose we go and look at Venus. Venus is it's somewhat like us. Semi-major axis is about, we're 1, of course, and the Venus has an orbit of 0.72 astronomical units. Okay. The radius is about the same as ours, very nearly the same. The mass is more or less the same. The greatest elongation, that means as you watch Venus, here's the sun here, it goes this far and that far. 42 degrees is the maximum angle from the sun to Venus. So that tells you where it is in geometry. All right. All right, now, Venus's rotation is retrograde. It's very, very slow rotation. It's not clear why it should be so slow and why it should be retrograde, but it is a small amount. And let's look at another picture. Okay, here are some pictures of Venus. This is kind of crazy. Now, There have been Russian landers that landed on Venus 30 years ago. Remember that I told you it's very hot on Venus? The mean temperature is incredibly hot. So the lander knew it was really tough terrain and it won't survive. It took a bunch of pictures and sent them off quickly before it died. All right, here's a picture of it. This is its foot. All right, 10 centimeters. Now these pictures were not taken with a camera. They were taken with a this is fairly fancy image processing, taken from a radar mapping of the entire planet. It was mapped by a radar screen that was pointed down at the planet as a satellite orbited around Venus. Okay, let's, here's some examples. What is a crater? We see these craters all over the place. Crater is when a rock or a BB hits the planet coming in at high speed. It splashes a lot of material away. This one's going pretty fast, splashes material and leaves a crater and leaves a rim of junk that it threw out. So let's see what we can see if we look at this planet. Okay, here are some species. This is the meteorite crater in Arizona. Who's seen this? Okay. Nobody else has seen that? Jeez. I haven't seen it either, I'm sorry. What was it like? Big. See any iron in there? Uh-huh. All right, this is 50,000 years old. It came down here, bang. It made a big mess. And an asteroid, they think it was 50 meters across. Here is 200 meters, so it's a small fraction of that. And it left a crater around here. Okay, we'll talk about these more. Here's a crater Tycho on the moon. Looks just the same. Okay, exactly the same.
Our flight begins.
Okay, this is on the surface of Venus.
About the size of the Los Angeles.
Shoot. There's supposed to be some sound here, but how do I get the sound to work?
Moving southeast, we pause to observe a small.
No, this is a radar. These are radar pictures. They're a bit fake. All right. This is all terrain of Venus. Now, Venus is not something you want to look at. I mean, you can't look at it. It's a very, very hot planet. You can't really see anything in it. It's covered. Oh, shame.
Our path then zooms east over jagged ridges to a volcano with a fluted rim.
There's a tick. That's known as a tick. I don't know if it's volcanic or what. But these are pictures of Venus. They don't tell you much here.
Turning northeast, we leave this tortured area and head to 7 pancake-shaped.
All right. This is a volcanic something. Volcanic.
And average 15 miles.
It's very different. They don't see stuff like that. It's like sticky bubble lava came up to make that.
Our flight then continues to the west and ends near the rim of an impact crater.
That is a crater from an impact. All right, this is all right, so let's call it a day now. We'll go back and talk about Venus on Thursday. I guess I'm out of time.